Okay. Right, so let's get started. Okay, so yeah, so we're here right now and submodule 1.3. Okay, good afternoon, guys, and we'll continue with chapter 1. So we're still introducing some basic concepts and introducing what plant utility systems are. Okay, before we move to further details of each system. Okay, so now let's see some basic concepts again in basic definitions in energy conversion and also energy conservation. Now, okay, so sorry about that. Now, among the three forms of energy in process plants, which we have covered in the last meeting, so we have electrical energy, mechanical energy, and thermal energy or heat. So among the three forms of energy used in process plants, heat is perhaps the most intensively consumed, okay, and this encompasses processes such as distillation, evaporation, drying, endothermic reaction, high temperature reaction, and so on. Okay, so there are many many points of use of thermal energy in an average chemical processing plant. Okay, and heat is produced by direct conversion from energy source. For example, fuel, so by fuel combustion. Indirect conversion from heat transfer media, meaning there's a second fluid or second material that transfers the heat from the heat source to the heat to the point of use of the thermal energy. Okay. Steam, for example. Okay, so steam is a very good example of a heat transfer media. Other examples would include hot oil, for example, and electrical energy. Okay, so these are some visual examples of process heaters, which works by these principles. So this one here, for example, this is called a package boiler. Okay, and what we have here is not sort of a direct contact, but if we look at this this unit alone, so we have here a heat transfer from the flame that is created by the combustion of fuel to the water and steam mixture on the other side of the tube. Okay. And this one is hot oil heater. Okay, so here we have the heat transfer media is hot oil. So it's specific types of hydrocarbon that is suitable as a heat transfer media. It has a high heat capacity, it has high stability at high temperature, and so on. It's basically speaking, what we do in this type of heat energy supply, so we simply heat up the hot oil and then circulate the hot oil, high temperature hot oil to the point of use, have them heat up the process fluid, and then return it again to the heater. So this is a continuous, non-stop, closed loop type of heating. Okay, and this one is electric process heater. So on the inside are heating coils. So this is electrical coils, and this so this provides heating to the fluid inside the shell through electrical current. Okay, so that's an electric heater. Okay, an example of simple electrical heater, for example, maybe you guys have heard of heavy fuel oil, perhaps. So large ships, and also some process plants, they consume a heavy type of hydrocarbon fuel, which is called the fuel oil. Okay, sometimes some people call it marine fuel oil or heavy fuel oil, but these are fuels that has the consistency that looks like asphalt. It's between asphalt and molasses, so it's very thick. It doesn't flow easily at room temperature. So before it can be burned in a burner, then it has to be heated up. So the oil has to be preheated in order to make it flow through the piping and into the burner. And to heat up the fuel inside the tank, we usually people use electric heaters like this. Okay. Right. Now, the second type of energy is mechanical energy. So mechanical energy or energy mechanic is used in the conveyance, meaning the transport of or the transfer of solid materials. Okay. Conveyance on the term conveyance only refer to solid materials. It doesn't apply to fluids. Okay. Pumping and compression of fluids, mixing of materials, size reduction and size classification. Size classification means separation of different fractions of solids based on their size, particle size, or magnetic property, or also density. Okay. So pemisahan padat-padat. Okay. Now mechanical energy is produced by direct drive by prime movers. Okay. So a prime mover is, or the Indonesian term for it is penggerak mula. A prime mover is a unit that produces mechanical energy to begin with. Okay. So for example, a gas turbine, yeah, a gas turbine is a prime mover. An electric motor like this, okay, this is an electric motor. An electric motor is also a prime mover. A gasoline engine, a piston engine is also a prime mover. Okay. So this prime mover then moves or drives other equipment. Okay. So for example, here, the gas turbine. This is the gas turbine, and that's actually which one is which? I think this is the gas turbine. Okay. You remember Brayton cycle in your thermal class. So this is the prime mover is the gas turbine. This one is a compressor, a gas compressor. So this compressor is driven by this gas turbine. So we say in this case, the gas turbine is the primary mover for compressor. Ya. Jadi gas turbin ini adalah unit gas turbinnya, dan ini adalah unit kompresor. Ya. Kompresor tugasnya adalah tentu saja meningkatkan tekanan gas, suatu gas. Ya. Jadi dalam hal ini, gas turbin ini adalah prime movernya, penggerak mula dalam bahasa Indonesia. Ya. So this is the prime mover, and this prime mover drives, menggerakkan kompresor. Okay. So we say that this is a gas turbine driven compressor. Okay. Whereas in this case, so this electric motor, this is the prime mover. Jadi penggerak mulanya adalah motor listrik ini. Yeah. Oops, sorry, this one. This is the motor listrik. Okay, this is the electric motor, and this electric motor drives the whole assembly. That drives this chain that carries with it buckets. Ya, jadi motor listriknya menggerakkan rantai yang bergerak kontinu, yang dimana pada rantai ini terpasang keranjang-keranjang buckets. Ya. And this is used to transport solids to a different elevation, ke ketinggian yang berbeda. Okay. So in this case, on the right-hand side case, we say that this bucket elevator is driven by an electric motor as the prime mover. Okay. Okay. All right. Examples of process plants that relatively need more mechanical energy include air separation plant, okay, nitrogen oxygen plant, natural gas liquefaction. LNG plant is actually one big or one gigantic refrigerator, actually fridge. Mineral beneficiation plants, it involves a lot of crushing and size reduction and also size classification. So these plants are examples of process plants that needs more mechanical energy than other forms of energy. Okay. Examples of chemical plants that needs more electrical energy, okay, relatively more electrical energy, sorry. This includes electrochemical plants, such as chlor-alkali plant, aluminum smelter, and also other electrochemical industries. So any electrochemical industry, of course, requires more electrical energy compared to other forms of energy, okay, mechanical and thermal, right? Now, energy source is not always available in the needed form. So utilization of energy always involves conversion of energy from one form to another form. And remember from our discussion in the last meeting, conversion of one form of energy into another form is always followed by a decrease of energy quality and increase in entropy. Okay. The right-hand side table, this gives you a rough idea of what energy conversion in the process industry look like. For example, and this also gives you some numbers, efficiency numbers. So for example, the combustion of fuels. Now remember, the energy contained in fuels are chemical energy, okay? In the form of chemical bonds. And when we break these chemical bonds, we will obtain thermal energy. That's what happened in combustion. Okay, so fired furnace, yeah, tungku pembakaran, the efficiency of fired furnace is typically around 65%. Okay. In boilers, for example, in boiler, we have a combustion of fuel from chemical energy into thermal energy. Okay. Let's see what else. We have endothermic reaction, where we have conversion from thermal energy into chemical bond. So endothermic reaction, of course, you end up with an increase in chemical energy after the reaction, of course. Ya, karena reaksinya endothermic, maka energi dalam dari sistemnya akan meningkat setelah reaksi. And some other examples here, for example, steam turbine system. Okay. This one, notice the difference between steam turbine and steam turbine systems. Okay, so in a steam turbine, your control volume is just the turbine itself. So the stream going in is steam, yeah, and the thermal energy of the steam is used to drive the turbine. Okay, so we have a conversion from thermal energy into mechanical energy. If we just look at the turbine itself, the steam turbine. However, if we look at the entire steam turbine system, which includes the boiler, then the energy conversion, the overall energy conversion, is from chemical bonds in the fuel into mechanical energy of the steam turbine. Because this involves two steps. Okay, so from combustion of fuel into steam, and then from steam to mechanical energy of the turbine, and so on. Okay, I think you can. This is pretty. You can pretty much guess. You can pretty much go through the rest of this energy conversions. Okay. All right. There we go. This is a simplified flow diagram of energy conversions in chemical plant. Typically, we start from fuel. Okay. To date, we don't have any around the world. Okay, we don't have any significant number of chemical processing plants that works with nuclear energy, for example, or solar power, tenaga matahari. Okay, so this is a conventional chemical processing plant. So this would be the typical energy conversion happening in chemical processing plant. So we have fuel, we combust the fuel in the furnace, and the thermal energy can be used to generate steam. The steam is then used to power a steam turbine, to drive steam turbine, or the thermal energy from the fuel combustion can be used directly to drive gas turbine or diesel engine, okay, and so on and so forth. So out of these three prime movers, so these would be prime movers, we will obtain mechanical energy, which then can be used for various purposes. The mechanical energy, for example, can be used to drive electric generator, which produces electricity, or the mechanical energy can be used to drive other process equipment and so on. Okay. The steam from the boiler can not only be used in steam turbines, but it can also be used as a heating media, right? In heat exchangers throughout the chemical processing plants. Okay. And after you generate electric power here, then the power can be used as in electric heaters. You can use it to drive electric motors and so on. Okay, so and it all starts from fuel. So you can start to appreciate the strategic role of fuel in any chemical processing plant. Okay, and here, of course, we also have we call this imported electricity, imported utility. So anytime you guys hear the word imported utility, do not imagine, don't associate yourself with the notion of import being necessarily from outside of Indonesia. Imported utility means it comes from outside of the plant. That's it. Okay, it could even be from the neighboring plant, for example, sharing with the neighboring plant. But in terms of the jargon in chemical processing plant, we say imported utility refers to any utility that is not provided or that is not self-generated by the plant, but has to be imported from outside of the plant. Okay, so we call it imported utility. Okay, all right. Any questions here? Not?
All good, sir.
Yeah. Okay. Good. All right. Now, so we talk about energy conversion, not to get our tongue tied. So this is energy conservation, conversion, conservation. Okay, that can be confusing a little bit. Okay? So in energy conservation, the big word is energy management. Okay, so we need to utilize energy as efficient as possible without degrading the quality or decreasing the quantity of the energy. So typically, these are what chemical processing plants typically do in order to save energy. And really, this has become a more pressing issue these days. Some of you may have heard about the trouble that we had, or are still having. I'm not really sure if we're still having that problem with the European Union for our export of palm oil to EU, to European Union, because they impose these environmentally related sanctions to us. Well, in a sense, they're blocking out. This is a trade war. Ini pada dasarnya perang dagang, gitu ya. So they're trying whatever legal way that they can impose to Indonesia to try to prevent our palm oil into reaching the European market. And one of the issues that they keep playing is, of course, the environment. Okay, it's an easy it is an easy finger to point at developing countries like us. Okay? But anyway, if we are not doing a good enough job in protecting our environment, then there is a finger that is fairly pointed at. Okay. So yeah, I mean, of course, in legal terms, it can be those issues can be used in a political manner to try to gain negotiation point. But if our country already do a good job at protecting the environment, then we shouldn't be worried about those those regulations. But anyway, this is a real issue for us in chemical engineers. I think other segments of industry will follow suit. The palm industry, meaning there will be more and more stringent environmentally related standards imposed to our products. Okay. Again, especially and most especially as relates to European market. So among all of the markets in the world, they're the one that is most sensitive to this kinds of issues. Okay. All right. So typically, chemical plants can do the following measures to try to reduce energy usage. They can try to reduce energy consumption by more intensive integration between main process operations and utilities. You will learn about this in a much greater detail next year in your Rancangan Pabrik, where you do what is called a pinch analysis, like a thermal pinch analysis. Essentially, what you do is trying to match the thermal profile, the heat exchange profile of the plant with the configuration of your heat exchangers. Okay. Number two, reduce energy consumptions by improving efficiency of equipment and to keep the efficiency at maximum level. Yeah. Replace energy-intensive equipment. That's number three. Number four, use high-quality feedstock to reduce load of feedstock or product purification, which usually requires much energy, but of course, higher quality feedstock comes at a higher price. Okay. Do overall improvements on the design of the processing system. Okay, so all of these efforts can be aimed at conserving energy. Now, typical steps in energy conservation programs. First, it is started by accounting of energy consumption on equipment level up to unit operations and unit processes level. Okay. Okay. So before we can do any measures, any energy reducing measures, we need to know what is our actual energy consumption is. Okay, so this is the first one here. This one here. Number two, observing and evaluating performance of equipment, operation unit, or processes. Meaning we are doing, this is called an energy audit. Oops, okay, what is wrong with this? Energy. There you go. Audit. Discipline supervision in all levels of operations. Yes, that's quite obvious. Energy conservation by improving process equipment involves changes in system design, at least change in equipment design. Okay, and these are some current topics in energy conservation. Okay, analysis and synthesis of steam system and work production. This is what I call the thermal pinch technology. Analysis and analysis and synthesis of heat transfer network. So this is the pinch technology stuff that I just told you about. Development of heat recovery units, and this one I think is probably of the three approaches here. I think this one is the most popular these days. I'm not saying one is more important than the others, but this one is simply more popular these days. Okay, development of heat recovery units. So trying to recover as much waste heat as possible from our process. Okay. So yeah, I can give you an example of this one. Well, perhaps not from the chemical processing industry, but there's one place that I remember on top of my head that develops this pretty interesting system for heat recovery. It's no surprise these days. I mean, this is not really high-tech stuff, but it's rarely practiced in Indonesia. So I'm sure you guys have heard that there's a hotel called Novotel in Ciamplas. Okay, so Novotel in Ciamplas actually has a system that captures the heat from their exhaust, their AC exhaust, yeah, panas buangan air conditioner, and then this waste heat from their air conditioners is used to warm up shower water. Okay. And this especially helps during the daylight. Ya, jadi pada saat udara agak panas, banyak orang di hotel menyalakan AC, kemudian panas buangan dari AC ini digunakan untuk menghangatkan air untuk mandi. It cannot be really hot because again, because the quality of the heat provided by the AC exhaust is low. The temperature is not very high, but it's good enough. It's high enough to produce warm water, which is comfortable to use for showers. Okay, but I think during nighttime they switch to just regular gas heaters or electric heaters. That system only works at daylight, where people tend to turn on their ACs. Okay. Okay. Another example. This is the energy conservation in steam power plant. Okay, so PLTU, pembangkit listrik tenaga uap. Now a power plant actually can be a standalone plant, or they can be a part of a bigger. Sorry about that. There you go. So a power plant can be a standalone or part of a process plant. Okay, it can be regarded as an individual plant with main product of electricity or process steam. Ya, jadi yang namanya PLTU ini bisa berdiri sendiri, ya, atau dia bisa merupakan bagian dari suatu pabrik yang lebih besar. Ya. Apapun itu, dalam analisis kita, PLTU bisa dianggap sebagai suatu pabrik yang berdiri sendiri, ya, dengan produk utamanya berupa listrik, ya, dan atau proses steam, ya, menghasilkan uap. Okay. In energy plant, engineers have their own roles in the design, development, and operation of the plant, of course, yeah. And every engineer must understand his or her task, obligation, and role in a team environment. Ya, jadi pada dasarnya semua engineer itu akan memiliki kewajiban sendiri-sendiri dalam suatu pabrik kimia. Masing-masing dari engineer ini harus paham tanggung jawabnya apa, dan juga team goals-nya juga harus mereka pahami dengan baik. Ya. This is the control room of a modern steam power plant, okay, steam electric power plant. This is a closer view of boiler of one of PLTU in Indonesia. I think this one is in Python. This one is also in Python. Okay, I think no, that doesn't look like Python. Not sure which one is this. Anyway, this is a major steam power plant in Java. It's either Python or Suralaya, either one of those. Okay, and you can see here this is a coal stockyard. Okay, now let me give you an advice, and this doesn't necessarily apply only to this class, but this is for your knowledge and for your further study here. Okay, because sometimes the student makes a really stupid mistake. Okay, whenever you see pictures of chemical processing plants here, don't just take a look at it and don't just admire the beauty of the chemical processing plant, okay? But try to figure out what's going on here, okay? So an example here would be this pile of black stuff here. So this is coal. Ini batu bara, ya. So this is called a coal stockyard, yeah. Sometimes people call it coal stockpile or stockyard, yeah. Pile usually refers to this mass of material here, and yard refers to the entire facility. Okay, so stockyard or stockpile, doesn't matter. And these are barges, tongkang. Okay, so these are barges that carries the coal from Kalimantan, from elsewhere. Okay, so these barges, they don't have any motors, they don't have any prime mover. Okay, they don't have any engine, so they're pulled by these boats, tugboats, kapal tunda. Okay, so they come through the sea, pulled by tugboats, and then they are moored, they're moored in this on these piers or jetties, and then the coal is sucked by an elevator system, and then it's deposited in this stockpile here, in this coal yard here. Now, try to be more watchful, okay? Be more curious and take a look at it here. So, what is the common way of storing chemicals that you know of? Biasanya zat kimia disimpan dalam apa biasanya?
Ada beberapa, bisa seperti dalam silinder, tank, atau pipeline.
Sure, yeah. If it's fluid, it's usually stored in closed tanks. Okay, cylindrical, it could be cylindrical or not, but usually if it's fluid, it is stored in tanks. Now, when it comes to solids, the way to store solids on site is a little bit more varied. Okay, sometimes you can store solids in a tank-like structure, which is called silo. Okay, but sometimes you can simply put the material outside on piles like this, dalam tumpukan. Okay. Now, can anybody guess or can anybody answer the reason why coal is stored like this? What happens if you store coal in a tank, for example?
It's far cheaper like this.
Yes, that's one reason. This is obviously much cheaper than any type of enclosed storage. All you need to have is a flat paved land, that is reinforced by concrete, right? With some, of course, there's industrial standards for stockpile, but basically it's just an open space with boundaries. Okay, so it's cheap. Is there any other reason?
Coal is like fairly unreactive, so you could store it out in the open.
Actually, quite the contrary. Actually, it is safer to keep it outside, exposed to open air, precisely because it is flammable. So coal is actually quite reactive. Coal is a dangerous. Actually, the reason why you cannot keep coal in a closed space, because if the closed space is heated up by sunlight, for example, your coal can spontaneously combust. Okay, so actually it is safer to keep it outside like this, exposed to the rain. Okay, but you cannot just leave it like that for weeks on end and not expecting that there's any fire inside it. Again, coal is actually quite a dangerous substance if you keep it in a large quantity. Okay, so in order to avoid bara api, okay, in order to avoid spontaneous fire, so every certain period of time, actually, this pile of coal needs to be turned over. Harus dibalik-balik. So they use heavy equipment, peralatan berat, bulldozers or excavators, to turn this pile around inside out. Okay, and the point is to circulate air throughout the pile of coal to prevent thermal buildup, to prevent temperature increase, which if becomes too high, it will ignite the interior of the pile, and that can be very dangerous. Okay. So now you can imagine if you keep this in a closed environment, then it will be even more difficult to perform that stockpile turnaround. Okay. So that is the reason why we keep coal simply outside like this. You don't even have to put roof on top of it. Okay. Just let it rain. If it rains well, so it will soak up some water. It will consume some energy, but it's still more economical than building a roof on top of it. Okay. Okay. So do not do what one of my rancangan pabrik advice did several years ago, where they designed coal storage in the form of aluminum tanks. Okay. And I said, okay, question number one is why tank? Question number two, why aluminum? Okay. The tank itself is not reasonable to be used with coal, and aluminum is way more expensive than stainless steel. And so I'm not sure where these guys get their idea that it's good to store coal inside an aluminum tank. That just doesn't make any sense. Okay. All right. I'm just gonna skip that one. Okay, some visual examples and state of the art. Right? And hopefully this will make you guys interested about utility systems and chemical processing plants in general. Okay. This is a an LNG plant, a small one actually. This is a, where is my, oh, there we go. This is a rather small LNG plant. Okay, so here, of course, that's the that's the LNG product tank, LNG storage. Yeah. Let's see, where do I start? This is purification section for the incoming gas, or the incoming feed gas. That's the amine unit, which is responsible to remove for the removal of carbon dioxide from the feed gas. That's the refrigeration compressors, and this one is where the fun starts. This is the liquefaction section of the natural gas. So this is where the conversion from gases, methane, into liquid methane happens. Okay. All right, and you can see here which units and operations require heat. Of course, well, of course we have to drive the entire plant, right? the core of any LNG plant is actually the primary compressor, okay, primary refrigeration compressor. So imagine this this plant is like a giant fridge in your house, okay, and if you listen to your fridge at home, then occasionally you will hear a mechanical whirring sound, right, or something like that. So that's that's your refrigerant compressor going on. And this is the one, that's the one here, okay? So this building here actually houses a set of refrigeration compressors. And if you remember your thermodynamics class, any refrigeration process relies on this compressor to move the fluids, okay, to change the PVT, the pressure, volume, and temperature state of the heat transfer of the refrigerants that enables refrigeration to go on, okay? So compressors need to be driven by something, right? Now, what drives this compressor? That question have more than one answer. Usually it depends on the size of your LNG plant. If your LNG plant is small, then this main compressor is usually driven by a gas turbine, okay? So the gas turbine acts as a prime mover for the compressor, for the refrigerant compressor, okay? In larger plant, usually the main compressors are driven by steam turbine. Yeah, that's what we have in the large LNG plants in Indonesia. For example, PT Badak and PT Arun when they were still operating years ago. Okay, so PT Badak uses steam turbine driven compressors. Okay. Yet even smaller LNGs, sometimes people make this, mini scale LNG units. So even very small LNG units can perhaps be driven by electric motors. Okay. All right. Okay. And again, another example of cooling system for process cooling. Okay. You might see this type of cooling system in public buildings before, right? Perhaps in hotels or in hospitals, okay? So this is called an air cooler. We call this a Finfet cooler, okay? And the reason for that funny name is that it has a fan, okay, kipas, and inside the pipes are equipped with fins, sirip-sirip, to increase the amount of heat transfer area. So thereby we call it Finfet cooler. Okay, so Finfet cooler is a simple, it's a very simple device. It cools down hot process fluid by using air, outside air. Okay, so this is this one here, it's air cooling. Okay, so this is that's the fan. Okay, this is the fan shaft, and this is the shroud to protect the fan, and the heat exchanger is actually this one here. Okay. Yeah. So these are the inlet and outlet flanges for the fluid that is being cooled down. Okay. This one is a cooling tower. We will learn about this. Pak Wawan will teach this in a much greater detail a few weeks down the road. This is a very very popular type of cooling system because it's very effective. Okay. This is called a closed circulation. No, not closed. This is an open circulation cooling. Okay. And the way cooling tower works is actually it evaporates some of the hot water. Okay. So some of the hot water is evaporated, and that evaporation will cool down the water itself. It's called an evaporative cooling. And that's what happened to our sweat when our body feels hot and and our skin excretes sweat. So it's not really the sweat itself that cools down our body, but when that sweat evaporates, okay, when water evaporates from the skin, that evaporation takes away some of the heat from our blood vessels, from our body. So actually, it is the evaporation of our sweat that creates cooling effect to our body. Okay, and this one is a one-screw cooling. Okay, one-screw cooling system pendinginan sekali lewat. Invariably, more often than not, one-screw cooling uses seawater usually, or any water body that is large enough. Typically it's sea. Okay, so in this type of warmth of cooling, the seawater is sucked in by the heat exchanger, and it changes its energy with it absorbs thermal energy from the process fluid, and then the seawater is returned to the environment. Okay, so it's not recirculated, but it's a once-through cooling system. Okay. So this is a cooling system. This is all of these that I'm showing you. These are considered to be utility systems. Okay, so you can start perhaps to guess that there are so many variations of utility systems, and that is 100% correct. And in fact, because there are so many specific types of cooling of utility systems, we don't have the time to discuss all of them in a one semester course. So we pick and choose the ones that we deem to be the most important. Okay, and hopefully you guys will learn to analyze the other systems that we did not cover in this class by learning what we have in this class. Okay. Okay, this one. This is a modern technology, relatively speaking. So this is a waste heat recovery system, and a typical waste heat recovery system looks something like this. Okay, so this one is some exhaust gas from somewhere, something. It could be exhaust gas from gas turbine. It could be exhaust gas from furnace. Ya, jadi ini adalah gas dari manapun. What is required from this gas is it needs to have a sufficiently high temperature to be able to effectively utilize as a waste heat, in a waste heat recovery system. Okay, so this is hot exhaust gas from somewhere. Okay, that is going to be ejected to the atmosphere. Okay, now you should also keep in mind that if we simply eject hot combustion gases to the atmosphere, not only are we wasting energy, but we're also harming the environment. Okay, there are certain standards for temperature of waste gas that can be ejected to the atmosphere. Okay, so we cannot just simply eject everything to the environment, including hot gases. Even though the gas is clean, even though the gas does not contain any toxic compounds, it doesn't contain. It contains an acceptably low amount of air pollutants, for example. But even then, if it is too hot, then it should not be ejected directly to the environment. It has to be cooled down first. Okay, so exhaust gas temperature is actually one of several environmental parameters, okay, in a chemical processing plant. So we need to somehow cool it down, and in the process of cooling it down, if we can extract that heat in an economical manner, then we will gain a double benefit, right? We get a cooler stack gas, and we gain something. We gain some energy from the stack gas. That's why it's called waste heat recovery system. Okay. So here, this is the exhaust gas, and this is the inlet transition. This is the heat recovery unit. Okay, and there are several technologies that are available to extract heat from the stack gas. You can use some heat transfer media, for example, thermal oil. This is a heating media. Okay, you can contact the gas with process fluid in a heat exchanger, for example. Anything that works. Okay. And this is the stack that has been cooled down because of this heat transfer. Yeah. So with an increasingly expensive fuel costs and rising concerns on greenhouse gas emissions from process plants, waste heat recovery is gaining importance. This is for sure. Okay. The waste heat can be used to heat process streams if it's not too hot, and or to heat transfer fluids. Okay, to heat transfer fluid. Okay, right? Which way that works. Okay. Sometimes if this the temperature of the exhaust gas is still very high, then you can actually use it to boil some steam. You can use it to create steam, and thereby from the steam you can use the steam to drive steam turbines, to generate electricity, and for other uses. Okay, so you can start to see that there are many ways to try to extract as much heat as possible, including this one here, ORC. Okay, organic Rankine cycle. This is a pretty big hype, right? Well, I shouldn't say hype. I don't mean to be to sound negative, but this is a new technology that has been gaining attention recently. It is still an immature technology, so it does not always work, but the concept is good. Okay, so on an organic Rankine cycle, as the name implies, this is just a Rankine cycle, okay, like the one that is applied in steam turbine, but instead of steam, it uses an organic liquid as the heat transfer media. So it is this organic liquid that is being boiled and then used to move turbines, and then condensed and then reboiled again, and so on and so forth in a Rankine cycle. Okay, so again, instead of water, instead of H2O, we have organic fluids circulating through the cycle. Okay, and the motivation of using this ORC technology is sometimes we have heat source, or waste heat source rather, that is which temperature is too low to be used to boil water. Okay, like the one that like the Novotel example. Okay, so heat that is released to the environment by air conditioning systems, the temperature is not very high. You can just try to if your house has an AC unit on it, turn it on, and then put your hand close to the condenser. Okay, you can feel that the air around the condenser is warm, but it's not very hot. Okay, so that's a sign of low temperature heat source or low quality heat source. That obviously cannot be used to boil water. Okay, so the idea is simple. So why not replace water with something that boils at a much lower temperature, right? So if water is replaced by organic fluids that boils at much lower temperatures, in this case, the boiling point can vary between -10 to 50 degrees Celsius for ORC technologies, then a Rankine cycle system can utilize the waste heat. Okay, pretty neat actually. The idea is pretty neat. Of course, organic fluids are much more expensive than water. It's more dangerous because these organic fluids tend to be flammable. But anyway, something's got to give, right? If you want something that works at low temperature, something that can extract heat at low temperature, then you cannot use water. Okay. All right. Any question here? So the ORC, this is the reason. This is the reason for the title here. Going for the low. We want to be able to extract heat from as low temperature as possible. Okay. You can even use the ORC to generate electricity right here. Okay, so this is used to generate electric power from this low quality waste heat. Okay. Right. Shall we continue? Now we're going for the high. Okay. In the last page, we're going for the low. Now we're going for the high. Ultra supercritical steam power plants. Now again, please go back to your thermal class and take a look at the Rankine cycles. Typical Rankine cycles in our textbooks. The operating envelope, ya. So this jadi daerah yang dilingkupi oleh kurva operasi ini ya, this operating envelope. The operating envelope does not reach supercritical condition. Okay, so the Rankine cycle that is in our textbooks is usually the one that is drawn in blue here, this one here, right? Okay. So from point 1 here, okay, start from here, expansion, and then yeah, that's expansion, reheat, expansion again, and then this one is pumping, I think. Yeah, there's one here, and then that's heat absorption, right? That's heat absorption, and this is the reheat. Okay, so the reheat during the reheat cycle. So what am I saying here? From the 6 to 1, that's just not reheat. This is the boiler. Okay, so going from 0.6 to 0.1 here, this is the boiler. Now, the Rankine cycle in our textbook is usually this one, the green one or the blue one. The point is their boiler operating condition is always subcritical here. It's below the peak of the dome here. So this is the critical point of water. Okay, so it's always here. So this is called a subcritical boiler, subcritical steam power plant. Yeah. But in today's technology, in order to improve the thermodynamic efficiency, then what people do is try to drive this boiler operating condition up. Okay. So they increase the temperature and the pressure of the boiler to this orange curve here. This is called a supercritical. Okay, supercritical boiler, supercritical steam power plants. Okay, the orange curve here. Okay, as you can see, if you follow the orange curve from 0.6 to 1, you can see that the curve totally lies outside the two-phase dome. Okay, this one here, right? And the latest technology is actually going even higher in terms of boiler pressure and temperature. So it is called an ultra supercritical. Okay, ultra supercritical steam power plants. It's this this purple curve here. Okay, this one. Okay, it goes from there, 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 and so on. Okay. This is a large ultra supercritical steam power plant in China. So I think right now China is operates the most number of ultra supercritical steam power plants, and this is actually so effectively their steam power plants is actually more efficient than Indonesian steam power plants. So Indonesian steam power plants now is still in supercritical stage. We're not yet at ultra supercritical. Okay. So again, the modern trend is basically the modern trend in conventional steam power plants. That is a shift towards ever higher PNT, okay, which will improve the thermodynamic cycle efficiency. Now, can anybody tell me what is the penalty or what is the risk of going for the high here, going for the high pressure and temperature in a boiler? This is the upside, right? The upside is we get an increase in cycle efficiency, but is there any downside to this?
It costs more, sir?
Yes, in terms of what?
Perhaps energy?
No, not really. Actually, you gain a decrease in energy actually, because its thermodynamic cycle efficiency improves. You're correct about one thing. You're correct about this power plant being more expensive, but in terms of what? Why does it become more expensive?
Can I add, sir?
Yeah, sure.
Since you increase pressure and temperature, then yeah, like if you increase more pressure, it means more money needed. And for temperature, maybe the containment, since like you use more about a higher temperature, so you have to like maybe use thicker walls or something like that, Mr.
Correct. Yes. So as you increase PNT, as you go for the high, then you will pay the price in terms of construction materials. Okay, so everything you need thicker walls, you need thicker metals, you need thicker refractories or insulation, you need more expensive exotic alloys for the turbines. So everything gets more expensive in terms of materials of construction. Okay, so in other words, you gain a decrease in operating expense, biaya operasi, right? But you have to pay for it in an increase in investment cost. Ya, jadi biaya investasinya naik, pabriknya lebih mahal, materialnya lebih mahal, lebih berat, lebih tebal, ya. Tetapi biaya operasinya, in this case is energy cost, is decreased. Your fuel
Exchange, sir.
usage becomes more efficient. Yeah.
Is there an effect in the perhaps environmental aspect, sir?
Not directly, no. As long as, but good question, excellent question though. If you look at this simple photograph here, actually, so all the environment is concerned is whatever's coming out of the stack, right? So as long as we can keep everything within regulation, either by using waste heat recovery or everything, that should be fine. It should be okay. However, you do have a point there, in the sense that the risk is greater. So we're not saying that the environmental impact will be greater, but if anything wrong happens, the risk is higher because you have higher pressure, means higher risk, right? Higher risk of boiler explosion. As you increase boiler, as you go further high in boiler pressure and temperature, then your boiler system will be more prone to corrosion problem, right? And that means you need to add more chemicals to your water, okay, to prevent the corrosion. Yeah. As a rule, both corrosion and fouling, ya, jadi korosi dan pengerakan air, itu dua-duanya semakin parah kalau airnya semakin panas. Artinya untuk menghindari itu, kualitas airnya harus lebih bagus lagi. And to guarantee that you do not incur corrosion and fouling, you need to add more chemicals to your water, to the boiler feed water. So more chemicals coming into your plant means higher risk of those chemicals spilling to the environment. Again, we're talking about risk. We're not saying that that will happen, but we're talking about risk. Okay. So yeah, good question. So everything comes with a price. You have a higher, well, ya seperti sekarang ya, mobil listrik. Okay. So electric vehicle, is it actually more efficient in energy? Perhaps, but is it actually better for the environment? I don't know. If we take into account everything, it might not be as good as it looks. You know, you need to have a factory that builds fabricates the battery. You need chemicals for the battery, and when the battery comes to its end of life, you need somewhere to dispose of it properly. So I don't know, perhaps the risk is even greater actually to the environment if we use the electric vehicle. It really depends on your point of view. It really depends on the way you analyze systems. Okay. Okay. Yeah. The world is, is more complex than it seems, but I hope in a good way, in a fascinating way. All right. Thank you for the good questions. Okay, now let's take a look at what we have, what options we have for mechanical work generation. Okay. This is just some conventional examples. This would be the ones that you can easily spot when you do a plant tour or a kerja praktek or Kulker, for example. Hopefully you guys can do, real life offline Kulker in the near future. But anyway, so this is an amine plant, yeah. Amine unit, and the purpose of amine unit is typically to remove acid gases from the natural gas. Okay, acid gas would be hydrogen sulfide, carbon dioxide, and so on. So, and one of the most important piece of equipment in an amine plant is this circulation pump. Okay, because if the amine circulation pump stops, yeah, and then your separation process will stop, your gas processing plant needs to be shut down, and everything. So it cascades down to a total shutdown of the plant if this amine circulation pump stops. So more often than not, people install more than one pump when it comes to amine circulation. So if one pump runs into trouble, the other pump can act as a backup. Okay. Sometimes they even install 3 amine pumps. Okay, believe it or not, in a large plants they install 3 amine pumps. So usually 2 is working and 1 is on standby. Okay, so the 2 pumps that are working, they don't even work at 100% capacity. They probably only work at 30%, 40% capacity. Okay. Again, that's to maximize reliability, to decrease as much as possible the possibility, the chance of the amine circulation stops. Okay. That's how important amine circulation is. Okay, let's see. This one is this is a gas turbine. This is a gas turbine driven compressor that is undergoing maintenance. Now, what I want to show you guys here, first of all, okay, so this is the gas turbine. Okay, so the gas turbine itself is this is from here to there. Okay, so this is the gas turbine, right? And this is the green colored equipment here. This is the compressor. This is the gas compressor that is being driven, yang digerakkan oleh turbin gas. Yeah. And this gas turbine is undergoing maintenance. And what I would like to impress upon you guys here is how big the equipment is. Okay. This is somebody's coverall, and ini bajunya orang yang digantung di sini. So this is somebody's coverall, and you can see that the turbine is this one is quite big. Okay, and it's not even the biggest one. Okay, so this is big, but not the biggest one. So if you stand on this platform, you will probably be about this high. Okay, so your body height will probably from here to there probably. Okay, so yeah, this is quite big. Okay, this one is a steam turbine. Okay, this is a steam turbine that is driving a compressor in a petroleum refinery. So again, this is a relatively large steam turbine. Okay, this one is a small one. This is a small unit, engine driven. This is sorry about this. This is some industry jargon. When we say engine driven, we refer to piston engine. So this would be a small diesel engine or small petroleum engine. We call it engine driven. Okay, so that's the engine is somewhere behind the panel there. So that's this is the air filter for the engine. Okay, and this engine, this piston engine, is driving this slurry pump. Okay, and this entire unit is mounted on a skid. So this is called a skid. Yeah, skid mounted. Again, if you work in the oil and gas industry, for example, those guys use a lot of skid mounted equipment. Okay, because in an oil and gas business, particularly the upstream oil and gas business, not the downstream but the upstream, people need to be able to move equipment quickly around the field when they do this, when they do exploration, when they do well workover or well maintenance, then they need to be able to quickly move this equipment from side to side. Okay, slurry pump. This is usually used to remove slurry from drilling. Okay, when they perform well drilling, then the slurry can be removed by using this slurry pump. Okay, so skid mounting is good if you want a non-permanent structure. Okay, so if you want to build something that needs to be able to be removed quickly, okay, then a skid mounting is a good one. Okay. But of course, with skid mounting, you cannot do this with a large facility. Okay, so equipment that is put on skid are usually small ones. Okay. All right, so this is the end of chapter 1 introduction. Any questions here?
Excuse me, sir.
Yeah.
I was just thinking about the going low one earlier, where you replace the water in the Rankine cycle with an organic fluid.
Yeah.
Is that in the same principle as like a refrigerator, like the refrigeration cycle? Because like in a refrigerator or AC, you use like R134 or something like that.
Mm-hmm. No, not really. This is the same principle as steam turbine. Okay, this is almost the exact cycle as steam turbine, but instead of steam, it uses organic liquid. That's it. It's very simple technology. Okay. The objective is actually the same as a steam turbine. So the objective is actually to produce work here. Okay. Now, whether this work is used to generate electricity or to drive something, some mechanical equipment, that depends on the need. But the objective is to create, to generate mechanical work here. So this is exactly as the name implies. This is a Rankine cycle, just a regular Rankine cycle, but instead of water, you're using organic fluids. And when you change the working fluid, then of course this curve will change, right? Because this curve is the characteristic of the fluid. So a TS diagram, okay, the temperature entropy diagram for water, will look a lot different from TS diagram for these organic Rankine cycle fluids. Yeah. The key thing here is that being able to boil at low temperature. Okay. Right. Compare this to water, which boils at 100 degrees Celsius. So you can see why this ORC technology can be used to utilize low temperature heat sources. Okay.
All right, sir.
Thank
you.
Hopefully that answers your question.
Yep.
Sure. Yeah. Any other questions? This is a new technology, by the way. This is not something that is already in widespread use yet. Okay. Pak Wawan, Pak Hendra, do you have anything to add? Any announcement, things like that?
Maybe I have some additional statement, Pak, regarding the question from Dama, Pak. So Damalia asking about the supercritical boiler.
Okay, let me open up the.
Yeah, I think
Okay.
For a given output, the supercritical boiler will use kind of the lower fuel consumption, but due to the increase of the efficiency. So when we have the lower fuel consumptions, it means that it will reduce the amount of the fuel that can be combusted. So I think by using the supercritical boiler, it can lower the carbon emissions, even though it's not actually as kind of the significant, but there is actually slight reductions. Because I even read the literatures that the 10% improvement in the efficiency can actually come up to the reductions of more than 25% of the carbon dioxide. So I think by using the supercritical type of the boilers in steam power plant, I think it can slightly reduce the CO2 emissions.
That's really interesting, sir.
Yeah.
All right. Any other questions? Pak Wawan, do you have anything to add or any announcement? Where's Pak Wawan? He's off somewhere. Okay, that's all right.
I think parallel with other meetings.
Yes.
With Pertamina, Pak.
Okay. Okay, if there isn't any question, actually we finished early actually, and that's fine, because this is a short chapter anyway. This is only introduction to the course. So anyway, so what we will discuss in the coming weeks are, let me just remind you guys for a second here. Yeah, this one. Oh, we're supposed to, no. Are we supposed to cover industrial fuel this week? Wait. Oh, yes, I think we do. So yeah, bear with me for a few minutes. I'm not going to go through all the entire 2 hours. Okay, but anyway, just to keep the momentum going. Sorry about that. So we're not supposed to finish yet, but I will, since I have not tweaked the slides for the industrial fuel. So I'm just going to give you a quick overview. But what we will do, what we will discuss in the next meeting. So I'll do about 15 minutes. Because the way we organize the course materials this year is different from last year's. So that the consequence of that is I also have to rearrange the handouts. Okay. Fuel. There you go. That's fuel. Okay. Okay. So for the next meeting, we will discuss about fuels, and I think I will finish that in. Actually, I will finish that in 1 hour because there's not much to say as actually in terms of fuels. And of course, you guys can read about and can read those materials before the class anyway. So between now and the next class, I will reorganize these handouts and post it in EduNext. Okay, so in the next chapter, we will discuss some fundamentals about combustion chemistry. So this principle here that we need to have proper contact of fuel with the combustion air. There has to be a certain minimum temperature that's achieved before we can induce the combustion and so on. A little bit about combustion chemistry. Some terminologies that you need to be aware of: flash points, auto ignition point, and this is also useful not only for this class only, but also for safety. Okay, so these are all safety related characteristics of fuel which you should know. Okay, combustion stoichiometry, fuel analysis. Okay, we will go through some discussion about how we analyze fuel, how we characterize fuel. Okay. Combustion stoichiometry, I think that's pretty straightforward, right? Nothing surprising there. How we measure heat of combustion, how we state the heat of combustion, that has been some source of confusion there. Okay, how we calculate the lower heating value and higher heating value. How we measure heating value using a bomb calorimeter. Okay, and this is what I want to discuss a little bit more. Okay, which is the review of types of industrial fuels. Okay, so we have gaseous fuels, okay, which is generally the general characteristics of gaseous fuels are they are clean burning. So they produce the least amount of harmful emissions per unit energy that they generate. However, they're also the most difficult to store and to transport. Okay, so gaseous fuel, clean but difficult to transport, difficult to store. Okay, that's the general notion that we get from gaseous fuels. Okay. This is some details about natural gas, LNG, and other natural gas products. Okay, LPG. Okay, this is the stuff that your parents use in their kitchens every day. Liquefied petrol gas. So you guys will get a quick review about what is the chemical composition of LNG, what is the composition of LPG, biogas, okay, where biogas comes from, and their general characteristics. Liquid fuels, okay. So liquid fuel, the general notion of a liquid fuel is that they have intermediate everything. Okay, they have intermediate energy density. They are much easier to store and to transport than gaseous fuel, but they are not as easy to store as solid fuels. So everything is in between with liquid fuels. Okay, combustion can be clean or rather dirty. Okay, so for light liquid fuels, the combustion is generally clean, meaning you do not generate a lot of smoke, a lot of unburned carbon. But if you're talking about really heavy stuff, that looks like asphalt, okay? So heavy fuels can generate quite a bit of pollution, okay? And its combustion is usually not complete, okay? So thereby resulting in soot, celaga, or in smoke. Yeah. Okay, their heating value is medium. Okay, again, everything is in between with liquid fuels. So we have, petroleum liquid fuels. You will be familiarized with these terms here: fuel oil, marine fuel oil, heavy fuel oil. Okay, IDO is industrial diesel fuel, and so on. Kerosene is minyak tanah. Okay, this is the stuff that your grandparents or great grandparents use in their kitchens. Okay, it's no longer being used today. Some property correlation, okay, between, for example, between the viscosity and density of the liquid fuel and their heating value. Okay. Some visual examples of the fuel, right? So this is what I'm talking about here. So, for example, MFO, marine fuel oil, is very thick like this, whereas high-speed diesel, so HSD is high-speed diesel, at room temperature looks something like this. Okay. And then some non-petroleum liquid fuels, okay, tar sands, coal-derived fuel, alcohol, biodiesel, bioethanol. Okay, this is the fuel for the future, right? Renewables. Okay. And then we will discuss solid fuels. Okay, general characteristics: they have high energy content. So pound per pound, they carry more energy than either gaseous fuels or liquid fuels. But solid fuels are difficult to ignite. Okay. However, because they're difficult to ignite, they are relatively easy to store, okay, and easy to transport, okay, compared to liquid and gaseous fuels. Okay, they require particle size reduction before combustion. So you need to pulverize, you need to grind down, you need to mill solid fuels before you can combust them. Okay, unless you're talking about bakar sate. Okay, but if you're talking about industrial usage of industrial combustion, then you need to grind down these solid fuels first, please, before they can use practically. Okay, some overview about coal. This is nothing. This is Wikipedia stuff. Okay, nothing. So no surprises here. Coal resources in Indonesia. Now this one, part 3, will not be discussed next week, but this part will be moved to the next chapter, which is on boiler system. Okay. So this is the difference between, wait, let me double check that first. Well, actually, I was a little bit mistaken. So the here we go. Okay, so the combustion system will be moved to module 5. So we will stop the discussion about industrial fuels after the solid fuel. Okay, so this one is easy. The reason why we're putting the reason why we are allocating only a short amount of time to discuss about fuels is because most of the stuff that will be discussed in module number 2, you can read it yourself. Okay, it's mostly about theoretical stuff, descriptive information about fuels. So I will try to focus more on things that we do need to discuss. But for example, combustion chemistry, how to calculate LHV, HSV. But as far as characteristics of fuel, I think I'm pretty sure you can read those on your own. Okay. So that way we can still finish fuel and combustion system in week number 2. Okay. All right. Any questions here? And you can be sure that the materials for module 2 will be ready before the class. Okay. All right. Okay, if there isn't any question, we'll see you next week. No? Okay, thank you. We'll see you next week.
Thank you very much, sir, for today.
Yeah.
Thank you very much, sir.
Thank you for
Thank
all
you,
your
sir.
questions. That's a good. This is the way that I wanted our class to be. So we want you guys to be active, to be curious. Okay, and this is something to get excited about. Hopefully, not to be scared about. Okay, so I really appreciate all of your questions today. Okay, thank you very much. Okay, thank you. Bye now.
Thank you, Pak Miki.
Thank you. Excuse me.
Bye, sirs.
Yep. Bye.
Thank you, sirs.